So hello everybody. So we're going to look at how to download a crystal structure file using the UK National Data Science Service. So this is the PSDS. You just have to go to psds.ac.uk. To get free access, you have to either log on from a computer at college or log on from home using a VPN. So this website gives you access to a variety of different databases that might be useful for different parts of your degree program. But we're going to focus today on the ICSD. So that's the Inorganic Crystal Structure Database. So I just click on ICSD, and that takes me through to the front page of this database. So you can see there's quite a lot going on. So where should you start? So at least for me, the easiest thing is to click on chemistry. And so chemistry brings up a series of queries based on the chemistry of the system. So if you click on periodic table, as you may imagine, you get a periodic table. So you can choose your favorite elements. So today I'm going to choose zinc and oxygen. And I only want systems with those two elements. So I'm going to restrict the total number of elements to be just zinc and oxygen. I will click OK. That populates these search boxes. So in principle, you can add additional constraints, but today I'm just going to run with this. So I click Run Query. And what do I get? So I get 9 pages, so about 90 entries relating to the crystal structure of zinc oxide. So that's because many people have made zinc oxide in the lab. There's many different mineral samples, and they've each performed different types of diffraction experiments. So maybe at different pressures, at different temperatures. And each of these entries is a refined crystal structure. So I'm going to start with a 1969 entry, and I'm going to click on the first one here. And so here we have additional information. So I've clicked on an entry based on zinc oxide, which we know. Then we have ABC, alpha, beta, gamma. So we can see that A equals B is not equal to C, and we have 90, 90, 120. So just from the cell parameters, you can guess that this is a hexagonal unit cell. And we get the volume. We know that it was measured at room temperature and atmospheric pressure, and it's labeled as high quality. I'm not sure how that's actually defined. The structure type that's refined is wurtzite, which is a characteristic structure of zinc sulfide, so one of the two main polytypes. And you can see the space group is 186 and begins with P, so it's primitive. So hexagonal primitive unit cell. Z equals 2, so that refers to 2 formula units inside the unit cell. So we expect 4 atoms. This was the title of the paper. So remeasurement of the structure of hexagonal zinc oxide, and the DOI will bring you to that original publication. So here we have a simple visualization of the structure. If you click on interactive, you'll get something obviously interactive, so you can rotate and play around with. And this is I guess it's the simulated powder diffraction pattern. So this is something you'd be able to compare to if you performed a diffraction experiment on zinc oxide yourself. Okay, so I click on chemistry. That's just confirming the chemistry again. We have an AB compound. A equals Z in zinc, B equals oxygen. It's referred to as zinc oxide. The mineral is called zincite. And I guess in this case, it's synthetic. Okay. So then we have the published crystal structure data. So I guess this is what's reported in the paper. So we have the ABC, alpha, beta, gamma. We have 2 coordinates, one for zinc and one for oxygen. It's guessed the oxidation state, so zinc 2 plus, oxygen 2 minus. And then the coordinates are 1/3, 2/3, 0, 1/3, 2/3, 0.3825. So these are the positions of each of those atoms in fractional coordinates. The Wyckoff symbol tells you the number of atoms in the cell, so each of those positions corresponds to 2 atoms when you include the symmetry elements of that crystal, and each oxygen position corresponds to 2 atoms as well. So that's how you end up getting 4 atoms inside, so just due to the symmetry relations. But you don't need to worry too much about that. They've also standardized the data. So over time, perhaps crystallographic standards have changed since the 1960s. So there might be a different choice in origin, a different choice in alpha, beta, gamma. But in this case, it looks like it's the same. It gives you some simple analysis, so you can analyze angles and distances, and some additional what we call metadata, so experimental information related to the measurement. So referred to as single crystal. Any additional information? No, there's not. So that's everything you get in this entry, but what we want to do later is visualize this structure. So how would we do that? We need to download this information. The really good thing, you don't have to copy and paste all of this data here. We're just going to use the crystallographic information file, or CIF file. So simply export CIF. Do you want to allow downloads from this website? Okay. And voila. So we have oops, let's go away from my to-do list. Here we go. So I've just opened up this file in a text editor, so you can see what it looks like. So there's a lot of information related to the publication itself, related to the symmetry elements, and then related to the coordinates of the system. So everything is there for visualization software to read in this file and reproduce the 3D crystal structure.